Welcome everyone. I'm excited to kick off today's presentation with the topic of pump selection and sizing. On this first slide, you'll see the main focus areas, including design, formula, standards, and performance curves. Over the course of this session, we'll explore how to choose the right pump, size it correctly, and ensure it meets all necessary standards. So let's dive in and get started. Let's take a closer look at the centrifugal pump. First, we'll discuss the key formula used to determine its head, which is H. The formula is head equals P times eta times 1000, divided by rho times G times Q. This might look complex at first, but essentially it relates the power, efficiency, fluid density, gravity, and flow rate to the head produced by the pump. For example, if we have a flow rate of 30 cubic meters per hour and a head of 20 meters, the power P required is approximately 2.2 kilowatts. This gives us a practical sense of how the formula translates into real-world operation. Moving on, it's important to note that the design and manufacturing of these pumps adhere to international standards like ISO 5199, ISO 2858, and API 610. These standards ensure quality, safety, and performance consistency across different applications. Now let's talk about the pump curve. Typically, as the flow rate increases, the head decreases, resulting in a characteristic parabolic curve. This relationship is fundamental when selecting a pump for specific needs. Finally, regarding applications, centrifugal pumps are widely used in HVAC systems, for circulating chilled water, and in irrigation setups. They are versatile and reliable for moving fluids efficiently across various industries. So, understanding these core concepts helps us better appreciate how centrifugals operate and their role in different systems. Let's take a closer look at the vertical turbine pump. This type of pump is designed to handle high head applications, making it ideal for situations where water needs to be lifted from deep sources. The key to understanding its operation lies in the total dynamic head, or TDH, which we calculate using the formula: static head plus friction loss plus velocity head. Each of these components plays a crucial role in determining the pump's performance. Now, when we talk about standards, the API 610, specifically the V's type, sets the benchmark for these pumps. This ensures reliability and efficiency across different applications. Speaking of efficiency, these pumps are often multi-stage, which means they have multiple impellers working together. This design helps maintain stable efficiency even at high heads, which is really important for demanding applications. Where are these pumps typically used? You'll find them in deep wells, where they lift water from great depths, in cooling towers for industrial processes, and in municipal water supply systems. Their versatility and robustness make them a vital component in many water management and industrial systems. So, to sum up, the vertical turbine pump's design and standards ensure it performs reliably in high-head, demanding environments, connecting seamlessly with the overall theme of efficient and effective fluid handling solutions. Let's talk about submersible pumps. First, there's a key formula to understand their power needs. P equals rho times G times Q times H, divided by eta times 1000. Now, don't worry if that sounds technical. It's just a way to calculate how much power the pump requires based on fluid density, gravity, flow rate, and head height, adjusted for efficiency. It's also important to note that these pumps comply with standards like IEC 60034 for motors and ISO 9906 for testing, which ensure quality and performance. When looking at the pump curves, you'll see that the flow versus head curve is steeper compared to other types. This makes submersible pumps particularly effective in confined spaces where space is limited, but you still need reliable performance. In terms of applications, they're commonly used for drainage, sewage management, and boreholes. Their versatility and efficiency make them ideal for these demanding tasks. Overall, understanding these key points helps us appreciate why submersible pumps are such a vital component in fluid management systems, especially in challenging environments. Let's take a closer look at the positive displacement pump. The key formula here is Q equals N times V times. Now, Q represents the flow rate, which is how much fluid the pump moves. N is the pump's speed, measured in revolutions per second. V stands for the volume displaced per revolution, so how much fluid gets moved each turn, and is the volumetric efficiency, which accounts for any losses or inefficiencies in the process. It's important to note that there are standard classifications for these pumps. Rotary pumps follow the API 676 standard, while reciprocating pumps are covered under API 675. These standards help ensure quality and performance consistency. One of the defining features of positive displacement pumps is that they deliver nearly a constant flow, regardless of the head or pressure they are working against. This makes them ideal for applications where precise flow control is needed. Speaking of applications, you'll find these pumps commonly used in handling oil, viscous fluids like syrups or heavy oils, and for dousing where exact amounts are critical. Overall, positive displacement pumps are versatile and reliable, especially when you need steady flow and handling of challenging fluids. They play a crucial role in many industrial processes, aligning with our theme of efficient and precise fluid management. Now, let's take a closer look at the diaphragm pump. The key to understanding its operation lies in this fundamental formula: Q equals A times S times N times A to V. Here, Q represents the flow rate, which is what we're ultimately interested in. A stands for the diaphragm area, essentially the size of the diaphragm itself. S is the stroke, or how far the diaphragm moves back and forth during each cycle. N is the number of cycles per minute, giving us the pump's frequency. And A to V is the volumetric efficiency, accounting for any losses in the system. This formula helps us understand how these variables interact to determine the pump's output. The diaphragm pump is standardized under ISO 15783, which ensures consistency and quality in its design and manufacturing. If we look at the flow curve, you'll notice it produces a pulsating flow pattern. This characteristic makes it ideal for chemical dousing applications where precise, steady delivery is crucial. Speaking of applications, diaphragm pumps are commonly used for acid transfer and sludge handling. These tasks require reliable, controlled flow, and the pulsating nature of this pump makes it particularly effective. So, in the broader context of our presentation, understanding this pump's operation helps us appreciate its suitability for specific industrial processes, especially those demanding accuracy and reliability in fluid transfer. All right, let's take a closer look at the gear pump. The key to understanding its operation lies in this formula: Q equals pi times D squared times B times N times A to V, all divided by 4. Here, D represents the gear diameter, which is essentially the size of the gears, and B is the width of the gear teeth. N stands for the rotational speed in revolutions per minute, or RPM, and A to V is the volumetric efficiency, reflecting how effectively the pump moves fluid. This formula helps us calculate the flow rate, or Q, which is critical for designing or selecting a gear pump for specific applications. Now, when we look at standards, the API 676 is the recognized guideline for gear pumps, ensuring quality and consistency in design and performance. If we visualize the performance curve, it shows a linear relationship between the flow rate, Q, and the rotational speed. And this means that as you increase the RPM, the flow rate increases proportionally, assuming the head remains constant. Speaking of applications, gear pumps are widely used in lubricating systems where precise, steady flow is essential, as well as in oil transfer operations. Their reliable, predictable performance makes them a popular choice in these areas. So, in essence, understanding this formula and the pump's performance characteristics helps us select the right gear pump for our needs, ensuring efficient and reliable fluid transfer in various industrial settings. Let's walk through the pump selection guide. First, you'll want to determine the flow, often represented as Q, and the total head. These are critical because they define what your pump needs to handle in terms of volume and pressure. Next, identify the type of fluid you'll be working with, whether it's clean water, viscous fluids, or slurry. Knowing the fluid type helps in selecting a pump that can handle those specific conditions effectively. Then move on to selecting the pump type by consulting the characteristic curve. Each pump type has a specific curve showing its performance across different flow rates and heads, so this step is essential for matching the pump to your application's requirements. After that, verify the pump's efficiency, represented as eta, and ensure the NPSH, or net positive suction head, requirements are met to prevent cavitation issues. Lastly, make sure your selection complies with relevant standards. This could be API, ISO, or IEC standards, depending on your industry or project specifications. Now, let's quickly review the formula that ties all these factors together. Power, measured in kilowatts, is calculated as the product of the fluid density, gravity, flow rate, and head, divided by the efficiency and multiplied by 1,000. This equation helps you understand the power requirements based on your operating conditions. Remember, selecting the right pump isn't just about matching numbers. It's about understanding these key steps and ensuring your choice aligns with your system's demands. All right, let's take a closer look at the performance curves overview. On this chart, the x-axis represents flow, measured in cubic meters per hour, and the y-axis shows head in meters. These curves illustrate how different pump types perform under varying conditions. You'll see curves for centrifugal pumps, submersible pumps, PD pumps, and others. The key takeaway here is that centrifugal pumps are designed for variable flow. Their head decreases as flow increases. In contrast, positive displacement, or PD pumps, provide a more constant flow regardless of the head. This difference is crucial when selecting the right pump for a specific application, as it impacts efficiency and system performance. Understanding these curves helps us see how each pump behaves in real-world scenarios, which ties back to our overall theme of optimizing system design and efficiency. So, when choosing a pump, consider whether you need a variable flow or a constant flow, and use these curves as a guide to make an informed decision. So, to wrap things up, let's briefly review the key points we've covered. First, we looked at centrifugal pumps, which are typically used in general HVAC applications. These are versatile and efficient for moving fluids in heating, ventilation, and air conditioning systems. Next, we have vertical turbines, which are ideal for deep wells because they can handle high volumes of water from great depths. Then there's the submersible pump, commonly used for drainage purposes. These pumps operate underwater, making them perfect for dewatering or flood control. Moving on, positive displacement pumps are best suited for handling oil or highly viscous fluids. They provide a steady flow regardless of pressure variations. We also discussed diaphragm pumps, which are often used in chemical applications due to their ability to handle corrosive or aggressive liquids safely. Lastly, gear pumps are primarily used in lubrication systems, where they efficiently transfer oil or similar lubricants to reduce friction and wear. By understanding these different pump types and their specific applications, we can select the right solution for any system requirement. This overview ties back to the overall theme of understanding how each pump type plays a critical role in various industries.